Hello, so this is a video on logarithms. This is really for my enriched class in grade 11, but this could also be used as an introduction to logarithms in advanced functions in grade 12. But if you're in my enriched class, I just want to start with a warm-up because in 3.7 we talked about the inverse of a function. I know we did this as homework, but let me take it up quickly as a warm-up as well on how do we want to determine the inverse of a quadratic when it is in standard form. Okay, so the key thing that we want to do there is we need to convert a quadratic into vertex form so that we take the square root of it. We have a single incidence of x so that we can isolate it and determine what x is. So remember the steps to determine the inverse is that first of all we're going to convert the f of x into y. So that's going to be y is equal to 2x squared minus 16x plus 29. And then we want to kind of flip the x's and the y's. So here I'm going to get x is equal to 2y squared minus 16y plus 29. And here we want to, even though our variables are y, we want to complete the square on the y. So here we get x is equal to, so in order to complete the square, we need to factor out the a value first. And I'm going to introduce the square brackets. So we factor it out. We have y squared minus 8y. And then leave a bunch of room because we need to add or subtract something to complete the square. And then on the outside of the brackets, we still have the plus 29. So what it is that in order to determine what we need to add and subtract to y squared minus 8y, or really just add, to get that perfect square trinomial is that we take 8 and we divide by 2, which is 4. We want to square that, so it's just 16. So we need to add 16 and we need to subtract 16. So once we get here, again, the whole purpose of adding the 16 is that turns into a perfect square trinomial, which is going to be x minus 4 quantity squared minus 16 plus 29. And then now we want to distribute the 2 into the square bracket. So we get 2 times x minus 4 quantity squared minus 32 plus 29. So here we get x is equal to 2 times, oh, I switched my x's to y's along the point. Sorry, my mistake. Got so used to writing x's on the right. So we get y minus 4 here. So we get 2y minus 4 quantity squared minus 3. Okay, so now that we got to this point, let me clean that up a bit. So now that we got to this point, we want to isolate for the y. So here we need to add 3 to both sides. So we get x plus 3 is equal to 2 y minus 4 quantity squared. Then we need to divide both sides by 2. So we get y minus 4 quantity squared is equal to x plus 3 over 2. Then we want to take the square root of both sides. We did all that work to complete the square and now to isolate for our power. Just so that we can do the square root. And I strongly encourage you that as soon as you do the square root, so that you don't forget, we know that whenever we do a square root, we have a plus and a negative answer. In other words, we have 2 answers. So here we have y minus 4. So in other words, the square root sort of undoes the square. And we get is equal to plus or minus the square root of x plus 3 all over 2. And now to get y by itself, we need to add 4 to both sides. So our final answer is going to be 4 plus or minus the square root of x plus 3 over 2. So that is the inverse of f of x, which is 2x squared minus 16x plus 29. Okay, so now that I have this vertex form, we're going to talk a little bit about the domain and range. The nice thing about vertex form is that we could kind of see that really quickly. So if I just want to maybe come back to this equation over here. And then we're going to see what that graph kind of looks like. So if I was to sort of rewrite this, maybe I'll rewrite it over here. We can see that our original function really is f of x is equal to 2 x minus 4 quantity squared minus 3. Okay, so what does this graph looks like? Well, we know that it has a vertex at 4 comma negative 3. Okay, so here we know in this graph, because the a value is positive, so a is greater than 0, we know that this points upwards. So we could here determine the range So to me, the range is easier to determine if we can see the domain and range of our original function. Then it's easier to determine the range and domain of the inverse because it's flipped. So for the quadratic here, we know that the domain here is going to be x is all real numbers. And the range is y is all real numbers, but in this case, y has to be greater than or equal to, so our vertex here is at -3. So that's going to be that. So in order to determine the domain and range of the inverse, we kind of flipped it. So here, let's do the domain. That's going to be domains all real numbers, but in this case such that x is greater than or equal to -3. And our range is just the domain of our f of x. So in this case, it's just going to be y is all real numbers. Okay, so we want to graph this. One of the things that maybe we could do is take this equation over here, start plugging in x's and y's, and get our graph. I would encourage you that maybe if it's easier to graph the f of x, then it's easier to invert those points and then graph that. So let's take that strategy. Here we got x and y. Because we've got so much practice in graphing parabolas, let's just do that really quick. So there's my scale, 1, 2, 3. So we know the vertex here is at 4, -3. So 4, -3 over there. And I'm going to label that point because we want to be able to invert that point to get our the inverse of that function. So we have that, and then in our in f of x, I'm going to take one point on either side of my vertex and get new points for there. So here we get x is 4. Let's make x equals 5. So here we got 5 minus 4, which is going to be 1 squared times 2, is going to be 2 minus 3. So we're going to have a point 5, -1. So 5, -1. And I'm pretty sure I should get one similar at a -1 on the other side. But I'm going to do the math again, just to make sure I'm correct. So here I'm going to get 3 minus 4, which is going to be a -1. -1 squared is 1. 1 times 2 is 2, minus 3 is a -1 as well. So good, I double check my math there. And there's my parabola of f of x. Okay, so now that I have that, it's actually really easy to graph the inverse. I'll do that in red. Is that we want to take each of these points and sort of flip the x's and y. So let's start with the original vertex, 4, -3. That's going to turn into -3, 4. So -3 and 4 will be right there. We're going to turn, I forgot to label this other point that I had over here. This was 3 and -1. So since I just did that, let's flip that point. So that's going to be -1 and 3. So -1 and 3 would be right there. And 5, -1 turns into -1 and 5. It'll be right there. And we can see that we do have a sideways parabola. Okay? And if you are visually astute, remember that if we had this line, oops, let me try that again. Didn't quite stick. There we go. If we have this line y is equal to x, remember we're going to have like a mirror, a reflection across that line of our two graphs of f and f inverse. So let me label this graph here, f inverse of x. All right. So that's how we kind of go off and do that. And to me, because we're dealing with parabola, we've dealt with parabola so many times, it was just kind of easier for me to work with that in order to graph the actual inverse of it. Because using this equation over here can get kind of ugly. So today, for this lesson, we want to talk about logarithms. So there's a few things that we want to focus on about logarithms. Is we want to understand and explain what a logarithm is. And I will say that in itself is a little bit of a challenge, but hopefully it's not too bad. Next, once we have that understanding, is we want to write exponential expressions as logarithms and vice versa. So immediately we can kind of see that there is a relationship between logs and exponential functions or exponential expressions. All right. And last but not least, once we have some of that, is we're able to evaluate logarithms, and we're going to discover, just like there were exponential properties dealing with exponents, we're going to see that there's going to be properties when we deal with logarithms. But first, let's understand what a logarithm is. And this is why it's really important to us for understand what the inverse is. So again, the inverse is that we have a function f of x. So here, f of x is equal to some expression. right? Plus 1, let's say. So here, when we talk about the f inverse of x, it means that we take all the answers, I call them the answers that we have from the original function, and really what was the question or what was the value of x in order to get that answer. So there was a couple of properties that we discovered from that is that if we take the f of x, but we take the inverse of that, we're actually going to get back to x, okay? Or we could say we take f of, and we take the inverse of x, but then we apply a function to it, we're also going to get back to x, all right? So there's a couple of those properties that's going to help us understand a little bit underneath about the logarithms, about that property of inverse functions, okay? So what we really want to do is look at an exponential function. So here we got f of x is equal to 2 to the power of x. So we want to determine what is the inverse. What is the inverse? So in order to turn the inverse algebraically, remember we're going to go over here, we're going to say y is equal to 2 to the power of x. In other words, the answer to our equation is, given an exponent, what is that answer of 2 to the power of that exponent? That's what y is. So the inverse is we need to flip the x and the y. And then we need to isolate for y. And we've never done this before because it's like, well, wait a minute, the y is an exponent here, and how do we actually get there? So this is what we call the logarithm. So how we write this is that this is the log. So in this case, what's the base? The base is 2, okay? In this case, what we're taking the logarithm of is what our actual answer is to the exponent. So in this case, log x, and that's what y is. Okay, so in this case, this is how we isolate for y is what we call the logarithm of base 2 of x, all right? So we'll go through some more examples beneath, but let's look at, some of the graph properties of it. So here we want to determine the domain and range of the inverse. But to me, sometimes it's easier if we look at the f of x to begin with. So let's look at f of x. We know that's our base exponential function of 2 to the power of x. Let's come up with a table of values. So we could graph this appropriately. So we have x 2 to the power of x. Again, I like to start at 0, 1, 2. Work the other way, -1, -2. So 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 squared is 4. 2 to the power of -1 is a half, because that's really negative exponent means we flip our base or reciprocate our base. That's going to be 1 over 2 to the power of 1. And likewise, 2 to the power of -2, that's going to be the same thing as 1/2 squared, which is 1/4. We know that when we graph the reciprocal, sorry, not the reciprocal, the exponential function, let me do the scale here. And then we maybe graph this in purple. We know that this had a horizontal asymptote along the x-axis, or in this case, y is equal to 0. And let's plot 0, 1, 1, 2, 2, 4. And then we have some points at -1.5 and -2.25. And we see that this graph, remember that's what the exponential function looks like. So there's f of x is equal to 2 to the power of x. That's what that graph looks like. And remember, we talked about exponential function is the fastest growing function of any polynomial. And we can kind of see that the right end is going to go up really, really quick because the exponent is growing. The exponent is growing. In other words, taking our previous answer, in this case, we're doubling it every single time, which grows pretty fast. So what does the inverse look like? Well, now that we have f of x, we're graphing the inverses that we're flipping their x and the y's, okay? So what we're going to discover is that here we're going to get a vertical asymptote. And let me try to do this in a different color, maybe in brown. Is that here we're going to get a vertical asymptote. Oh, I want to do the highlighter. Sorry. Let me do this in red. Okay, so there's a vertical asymptote, and that's going to be at x equals 0. All right? So we want to graph the inverse. So let's start at 1, 0. So 1, 0 is going to be right there. Then we're going to have 2, 1. So again, how to get 1, 0 is I'm flipping my x's and my y's. So now I got 2, 1. So 2 comma 1 looks like that. And then 4 comma 2. So 4 comma 2 is going to be looking like that. And then going the other way, I'm going to half and -1. So 1/2 and -1 might be right there. And you get a quarter and -2. And we're going to see that we keep going down. We get an eighth, a 16th, etc., etc., etc. But again, we're never ever going to hit 0. So that's why we have a vertical asymptote. And that's what my f inverse of x is. Okay, so in this case, the inverse of my exponential function is a log. What is the base of my exponent? It's 2, and we're taking log x there. All right, so that's what the inverse is. And if we draw a line y is equal to x, so let me draw that over here. Y is equal to x. We can see that the green and the purple graphs are sort of a mirror image of one another along that. All right. So that's what kind of the logarithm looks like. But you know, to us, it's like we want to also understand the numeracy of it. How does it affect things? So really, a log is the inverse of an exponential function. It's called a logarithm, a log for short, as we see above. So in general, if we have x is equal to b to the power of y, then we say that y is the logarithm of x to the base b. And I like to think of it as, what is the exponent? So really, logarithm is determining the answers. What is the exponent given a certain base b, and what our actual value that we're looking for there is. In this case, it's x. All right. So it looks like this. So that is log base. Our base is b. What's the answer to our power? So in that case, that's going to be x. And the actual answer to that is the exponent. Okay, so really, if we think about exponential functions or exponential equation, the answer is that power. But when we look at logarithms, we're given the answer, but we want to know what exponent gives us that answer to that base. All right. So things about notations, as I mentioned many times, mathematicians are lazy. So we take a logarithm of base 10 a lot. And so that's why when we see something like this, log of 7, the implication that the base there is actually 10. Okay, so this is no different than why we never write the exponent 1, or when we do a square root, we never write the radix 2, because this happens so much that it's going to be just implied if it's not written. All right, so that's an important thing to keep in mind. All right, so let's go through some of these examples to get a better understanding of what a log is. So we're going to write each of the following exponential expressions to equivalent logarithm. All right, so it just starts as simple as this: log. Well, in my power, what is the base? In this case, it's 25. What is the answer to my power? In this case, that's 5. And the answer to the logarithm is the actual exponent. So what we're saying is that 25 to the power of what is equal to 5? And basically, that's like the square root, so that's going to be a half. All right, so let's rewrite this power. Okay, so here we're going to go log. What's my base? Is 4. What's the answer to my power? 64. Well, 4 to the power of what? You can think about that. Gives me 64. Well, the answer is my exponent, which is 3. All right. So here, let's write out this one. We got log. So my base here is 3. What is the actual answer to my power? In this case, is 1 over 81. And what's the exponent that gets us there is going to be a -4. And we can kind of see that the exponent should be negative because my base is 3, but we get a fractional answer. We get an answer that's a fraction. So we have to reciprocate our base, so turn that into a third, and then 3 to the power of 4 is actually 81. So you can kind of see how that goes. Next one is one that applies to one of our log rules or laws. Here we have log. Well, what's my base is 11. What's my answer? 11. Well, anything to the power of what exponent gives me that same answer? Well, our exponent here is always going to be 1. All right. So in this case, now we want to go back to the opposite, the other way. So now we're given a logarithm. How can we write the equivalent exponential expression? So given log base 10 of 100 is 2. What's my base here? That's going to be 10. Oops. That's going to be 10. what's the actual answer to my log gives me the exponent. In this case, it's 2. And what I'm taking the log of is the answer to that power. In this case, this is 100. And this one makes a little bit more sense because we're used to deal with exponential expressions. So 10 squared is 100. Let's look at the next example. My base here is 3. Remember, the answer to the log is my actual exponent. And then what I'm taking the log of is the answer of my power. So in this case, it's 1 over 27. And we do see that 3 to the power of a negative a third, which is going to be 1/3 to the power of 3, which will be 1 over 27. Okay, our next example, we have log base 5. So that means that's the base. 5 is the base of our exponent. Remember, the answer to our log is our exponent. And what we're taking the log of is the answer of the actual exponential expression. So here we do see 5 to the power of 0 is 1. So that makes sense. So in general, when we have something like this, here, what's the base of my log? That's h. Remember, the answer to the log is my actual exponent. So in this case is m. And k, what we're taking the log of is the actual answer of the exponential expression. All right? So let's work through some examples where we actually evaluate. So really, when we take a look at log base 2 of 32, really we're trying to say 2 to the power of what is equal to 32. Okay, so here we could break down 32, recognize that 32 is 2 to the power of 5. So really that implies now that x is equal to 5. All right, so we're going to apply the same thing over here. Log base 3 of 27 is going to be 3 to the power of what? In other words, what we're trying to solve for is 27. And here we can see that, well, 27 is going to be 3 cubed. So that implies that x is going to be 3. Okay, so we're supposed to show some examples in here where we could see the answer is going to be, I don't want to say a perfect power, where it comes out nice, so that we could get to the same base and kind of easily determine what the exponent is. Later on in the lesson, we're going to see that, well, sometimes that's not going to work out. So how do we actually get an answer to this, right? In other words, what happens if it's log base 3 of 29? Because nothing, 3 to the power of not an integer is going to give me 29. We know it's going to be a little bit greater than 3. We're going to discover how we could actually get that answer. All right, next question we got, so our base here is 4. Again, we don't know what the exponent is, over 1 over 64. Okay, so this one's a little bit tricky because I kind of see we need to do with the negative exponent. So here we're going to say 4x. Well, first of all, 1 over 64. Well, 64 is the same thing as, I believe, 4 cubed. 4 times 4 is 16 times 4 is 64. So here, that means this is going to be 4x, the same thing as 4 to the power of negative 3. So that implies that x is equal to negative 3. All right. Next example is a little bit tricky, because here we're going to have log base 6. So 6 to the power of x is equal to 36 to the power of 4. Remember, our base is 6. Our actual answer here is 36 to the power of 4. So the trick here is we want 36 and 6 to have the same base. So here we get 6 to the power of x is the same thing as 6 squared, because 6 squared is 36 to the power of 4. So 6 to the power of x is the same thing as 6 to the power of 8, applying our power laws. So that means x is equal to 8. All right. So that's working through that, just as a good understanding in it. I'll be honest, it takes a little while to sort of think backwards, if we want to call that, or really undoing the exponential function. Really trying to think of the log as what is that? The answer is the exponent. Like what we were looking for is what is the exponent that gives us that answer to the power. And in this case, we're given the answer to the power. And that's what the definition of a log is. All right. So let's look at some properties, and hopefully this kind of makes sense. I'm going to look at this one first. Here we're going to say the log base a of a to the power of x, right? So here we're saying, well, here's our base, here's our actual answer, a to the power of x. Well, what's the exponent on that? Well, if we have a, notice that the a, we have the same base in our log and the same base of our power, so the answer is just our exponent, okay? Looking at the other way around on this one, this is a little bit more tricky, but here we're saying that a to the power of log base a of x is just x. All right, in other words, we're sort of undoing the exponential when we got x there. This is the one where we have f of. So we think of the exponential function as f of, but now we take the inverse of it, which is the log of x, which is going to give us x. And this one over here is actually the opposite. If we take the inverse, because that's what the log is, of our exponential function, which is f of x, then we get back to x. All right. This one, I think we just had an example of this. No, there's four that we had. So this one we're saying, given a base, and then given an answer 1, what's the exponent? And we know that, well, anything to the power of 0 is always going to give us 1. So that's what this one is trying to say, except here that a can't be 1 in this case. All right. Last but not least, this one had an explicit example. Here we have the base, and our actual answer is the same as the base. In other words, what's the exponent? Given any number, it's going to be the exponent is 1. All right. So that's some of the logarithm properties that's kind of coming out of this. Let's go off and evaluate some things. I think this is similar to what we did above, but let's go through this. So here, log 4 base 16. Log base 4 of 16. So this is going to be like 4 to the power of x is equal to 16. And we know that 4 to the power of x, so 16 is just 4 squared. So here we can apply that x is equal to 2. Over here, we're going to get log base 3 of 127. So 3 to the power of what is equal to 1 over 27. So here, I'm going to convert 27 to the power of 3. So 3x is equal to 1 over 3 cubed. But here I want to bring up the exponent, so to speak. So here we get 3x is equal to 3 to the power of negative 3. So that implies that x is equal to negative 3. Okay? So again, the trick here is that because we have our base, you can think of this as really 1/3 to the power of 3. Okay? We normally write it like this because 1 to the power of anything is just 1. But we could rewrite this as 1 over 3 to the power of 3. But we want a negative, so in other words, we want the base of 3. So we reciprocate a third to get 3. And that gives us a negative exponent. All right? This one over here, this one, let's take a look at this one slowly. So here our base is 5 to the power of x. In other words, we don't know what x is. But that gives it the answer of square root of 125. But we could sort of convert. So this is a lesson on our radical rational exponents. Is that, well, 125 is really 5 cubed, right? And then 5 to the power x. Well, remember this had a radix 2. We don't write the radix of 2 as square root, but we're going to turn this to rational exponent. This is going to be 5 to the power of 3 over 2. And therefore, we can apply that x is 3 over 2. Here's some more examples that we're going to work through. So log base 4 of 4. So this is 4 to the power of x is equal to 4. Well, this is our law that we had over up here. That log of the base is equal to 1, if that made sense. So this one is the same thing. I'm not sure we're asking it twice, but here that implies that x equals 1. Log, so this one, log base 12 to the power of x is equal to 1. So again, anything to the power of 0 is going to give us that answer 1. So in this case, x is going to be 0. In other words, 12 to the power of 0 is going to give us the answer 1. This one, it looks like, oh, what do I do? There's no base. So remember, we don't write the base 10. So this is really 10 to the power of x is equal to 10. So that implies that x is equal to 1. All right. So we want to rewrite each of these expressions as a logarithm and then determine y. So first is that we take this, because this looks weird. We have 3 to the power of log. So our log is in our exponent, all right? But what we want to do is just break down our power. So our power, here's our base, and there's our exponent. So if we take, what that means is that we take the log, well, what's our base? The base is 3. What are we taking the log of? Well, it's y. Y is the answer to my power. And then the log of that is my exponent. So in this case, my exponent is actually log base 3 of 7. So here we got log of base 3, log of base 3. So we have the same base of our log. So there we can apply that y is actually equal to 7. And that was applying the law that we had back up here where we had this. Okay, so this is how we sort of can derive that from an explicit example. And this one I think is going the other way that we had. So again, we want to convert this to a log. So there's my log. What's my base? My base is 7. And what's my answer to the power? So that's what the log is. And in this case, what is the exponent? Is log base 7 of 33. So again, I have the same base of my log. So therefore, I can apply that y is equal to 33. Okay. Now it comes a little bit more of a challenge because we know that we have exponential laws, but now we have logarithm laws. And this is how we might try to explore this a little bit. So here we're going to have log of 2, and the answer is 4. In other words, 2 to the power of x is equal to 4. So that implies that x is equal to 2, because it's going to be x squared is 4. Here we're going to say, well, 2 to the power of what is equal to 8, because that's the definition of a log. While in this case, in numeracy, we're going to apply that this is x is equal to 3, because 2 to the power of 3 is equal to 8. Well, what's log base 2 of 32? Well, that means 2 to the power of x is equal to 32. And 32, I think, is going to be like 2 to the power of 5. So here, 2 to the x is equal to 2 to the power of 5. So that implies that x is equal to 5. But we could actually look at this log as also log base 2 of 4 times 8. Right? And so what's the connection here is that we get the answer 5 of log of 32. But log of 8 is 3, and log of 4 is 2, all base 2. So what's the connection there? Kind of seeing that hinting at 2 plus 3 is equal to 5, right? But let's try that another example to see if that works. So log base 3 of 81, 3 times 3 is 9, times 3 is 27, so that's going to be 4. So in other words, we have to 3 to the power of 4 is 81. Log base 3 of 3, well, that's just going to be 1. So here we're going to say log of 243 base 3. Yes, this is the same thing as log of 81 times 3. Okay, but let's work it on our calculator. 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is going to be 243. So really, log of base 3 of 243 is 5. In other words, 3 to the power of 5 is equal to 243. And you can check that in your calculator. So we see that that property seems to going to be applied because 4 plus 1 is equal to 5 here as well. Okay, so that's one of the properties you can see when we're sort of multiplying and kind of hinting, breaking up what we're taking the log of, and we break that up to two different products. Is really going to be the sum of those logs. That's what we're going to say here. Well, let's look at it's going to work for division as well. Okay, so let's look at this example. Log base 2 of 32, we just said it was a 5. 2 to the power of 5 is 32. Log base 2 of 8 is going to be, well, that's going to be 3 because 2 cubed is 3. Well, what's the log of base 32 over 8? Well, this is really the same thing, a log of base 2 of 4, which is going to be 2 because 2 squared is 4. And we can kind of see that, well, it's kind of like the reverse is happening as well when we do division. Because here 5 minus 3 is equal to 2. Another example here is log base 3 of 27 is 3. Log base 3 of 9, that's going to be 3 squared, so that's going to be 2. But what's log of 3 of 27 over 9? This is going to be the same thing, a log base 3 of 27 divided by 9 is 3. So log base 3 of 3 is just 1. All right? So these are the properties that we're discovering, is that log base A of P times Q is going to be the same thing as log base A of P plus log base A of Q. Notice that it has to be, it's going to have the same base to our log. Likewise, when we do division, we're going to say that this is going to be log base A of P minus log base A of Q. And last but not least, we have this power. We think of it as a power law. So this one is actually really kind of funky. And it's kind of a hint to how we kind of get rid of an exponent, if we want to say that. Because we take a log of something, and then if the exponent is there, the property is that this is going to be the same thing as c times the log base A of P. And why does that work? Well, this is really an extension of this, because here we have log of A of P times P times P times P. In other words, C number of times. Well, this is going to be the same thing as log base A of P plus log base A of P plus log base A of P C times. So this is going to be C times the log base A of P. So that's how we sort of derive like the power version of the logarithm property. All right. So how do we go off and apply to some of these things mathematically? So here we got the same base. So here we could say that this is going to be the same thing as log base 8 of 32 times 2, right? So here's we're adding 2 logs, which is the same thing as the product of what we're taking the log of. So this is going to be the same thing as log base 8 of 64, and that's going to be 2, because 8 squared is 62. This one, we're going to have log. So here we have subtraction, so we could divide what we're taking the log of. So it's going to be 200 divided by 2. Remember, we don't write, or we don't see what the base is, so that's going to be applied to be 10. So this is the same thing as log base 10 of 100, which is 2 as well, because 10 squared is 100. Another example over here. So here we got 6 log 5 of 25 to power 6. Well, this is going to be the same thing as, well, one of the properties, we're going to take that 6 times log base 5. We're going to do this in 2 steps. So in this case, that's going to be 5 squared. 25 is 5 squared. So that's going to be 6 times log of 5 of base 5 squared. It's going to be 6 times 2, which is 12. All right. So this one, we kind of want to do the opposite. We can kind of see what's going on here. We could do this. It's not the only way that we can do this, but this is one way we could see it. It's log base 9. Well, we're going to actually move the 2 to make this 3 squared. So this is log base 9 of 9. Well, that's just going to be 1. Okay. Last but not least, here we're going to have log base 3 of the cube root of 9. So what does that look like? Well, this is going to be log base 3. Well, we're going to compute the cube root into a rational exponent, which is going to be 9 to the power of a third. So now that we got that, we could move the exponent outside. So we get 1/3 log base 3 of 9. So that's going to be 1/3. Well, log base 3 of 9, when there's 3 to the power of what is equal to 9, that's going to be 2. So here our answer is 2/3. Okay. Let's go through a last couple examples, and then a big conversion rule that's going to be really important for you to solve any log. So here we have 3 additions. Notice that here they're all base 10 because there is no base written for the log. So here let's kind of combine this into log of, well, 12 times 9, because we're adding, in this case, we divide by 2. So log base 10. So we want this as a single logarithm, so we don't want an answer for this. So this is going to be equal to log of, well, 6 and 2 cancel, so 6 times 9 is 54. So this is log base 10 of 54, but in our final answer for tech marks, we never want to write the 10 for there. You could write it as long as when you're doing your work. I don't have a problem with that. But in our final answer, we must write as log of 54. Okay. Next one, here we get a log base 3, but we're subtracting. So here this is going to be the same thing as log base 3 of x squared minus 1 over x plus 1. All right, now we want to simplify what's inside our brackets. So here we're going to log base 3. We're going to factor x squared plus 1 to be x plus 1 and x minus 1. Okay, so that was, there we go, a bracket over there over x plus 1. So here we're going to cancel. That was a little bit of a lesson from our last unit in terms of rational expressions. So in the end, we're going to get log base 3 of x minus 1. But please remember restrictions. In this case, x can't be negative 1, okay? Because that was a restriction that we had in our denominator of that, okay? You can almost kind of see log of 0, we can't take the log of 0. All right, because remember in our graph, can we ever get an answer 0? Like we can't take the log of 0 because we never hit there on our graph. All right, so that's another way to kind of see it. So conversion rule for a logarithm for any base to base 10. So this is really, really important because some of you might have fancy calculators. We could actually do a log. You can type in the base and you get the answer. But if you don't have a calculator that does that, here's our rule for doing it. And it reads like this. So log, you have a log base b of a. This is the same thing of log of a over log of b, all base 10. Okay? So in other words, how I like to think of it is if we have a power, y is equal to b to the power of x. If we want to know what that exponent is, what x is, then to me that's log of my answer over log of the base. That's how I remember it, log of my answer over log of my base. Okay? So in this case, we want to convert log 3 of 13. Was that one of our, no, that wasn't one of our answers. We should have done something. Well, that we could just plug in our calculator, log, because all calculators should have a log base 10. So here log 3 of 13, log base 3 of 13. That's the same thing, log base 10 of my answer, which is 13, over log of base 10 of my base, which is 3. So you put that into your calculator, we'll get an answer of 2.3347 roughly. Okay, so this is why you're given a question like this and you're allowed to use a calculator. This is how you get the exact answer. All right, so there's our lesson on logarithms. I'm hoping that it was somewhat clear and hopefully definitely helpful.